There's this really interesting paradox right at the heart of computer science. Our minds, they're creative, they're flexible, but the computers we build, they demand rigid, perfect, step-by-step logic. Today, we're going to explore a fascinating new approach that tries to build a bridge right across that gap, making the very foundation of reliable software, these things called formal proofs, more powerful and, believe it or not, more intuitive than they've ever been before.
Okay, so let's just start with a simple question. Think about it. We prove things to each other all the time, right? We use intuition, we give examples, we make these creative leaps. But how in the world do you convince a machine, a thing that demands absolute logical perfection, that your code or your theory is 100% correct? Yeah, it's a lot harder than it sounds.
And that question, that challenge, brings us right to the core of our topic today, what we can call the computer proof problem. There's this fundamental clash between the way our brains are wired to think and the way computers need to verify.
And what's so cool about this is how it just lays out the two sides of the coin. On one hand, you've got us, human reasoning. It's flexible, it's creative, it can even be a little bit messy, but hey, that's how we innovate. And on the other side, you've got the formal proofs that computers need. They're rigid, they're precise, and every single step has to be verifiable. They are worlds apart.
So, what's the big deal? The big deal is this gap. This chasm makes creating those formal proofs incredibly difficult for people. They end up being these clunky, unreadable, super hard to write things, and that actually slows down progress in creating the kind of perfectly reliable and secure systems we all want.
So, how do we fix it? Well, researchers are basically building a bridge across that gap, and it all starts with this idea of creating a more flexible language for proofs.
The magic word here is extensibility. So what is that? Well, imagine you're writing and you find yourself repeating the same complex idea over and over again. What if you could just invent a new word for it, right there on the spot? That's pretty much extensibility. It's the power for a user to customize and extend the proof language itself while they're using it.
And this slide just shows you the difference perfectly. On one side, you have traditional systems, something like Mizar. It has a fixed, unchanging structure. You have to play by its rules, no exceptions. But on the other side, you have these new extensible systems, like one we're going to talk about called SPL, that are designed to be adaptable. The user can actually define new syntax to make their own proofs clearer and more intuitive.
And that is the whole point. This flexibility, it's not just some neat party trick. It's a direct solution to the problem we've been talking about. It helps shrink that gap, making these formal, machine-readable proofs start to look and feel a lot more like the informal, human-readable arguments we're all used to.
Okay, that all sounds great in theory, but what does it actually look like when the rubber meets the road? Let's zoom in on a specific example and see this whole extensibility thing in action.
So let me introduce you to SPL. It stands for Simple Declarative Proof Language. It's this experimental language built on a really solid verification system that was designed specifically to test this idea. It's built from the ground up to be changed by the user, letting them shape the language to fit the problem instead of the other way around.
And the way it works is actually beautiful in its simplicity. First, a user spots a pattern in their proof that's either really complicated or just super repetitive. Then they define a new piece of custom syntax to simplify it. And finally, they can use that brand new syntax to write proofs that are way clearer and easier for anyone to understand.
And get this, it's not just an idea on a whiteboard. They actually tested this out. There was a big case study that applied SPL to the really complex field of group theory, and it proved that the approach works. It made the theory easier to handle and the proofs much more readable. That gives the whole concept some serious credibility.
Okay, so let's zoom out for a second. SPL and this whole idea of extensibility, they're actually part of a much bigger, even more ambitious quest happening in computer science. So when you look at the bigger picture, researchers in this field are really chasing two huge goals. The first is automation, basically getting computers to do more of the heavy lifting. And the second is unification, getting all the different proof systems to actually talk to each other and understand one another.
The quest for automation, it's all about what it sounds like, getting the computer to do more of the hard work. Using these specialized frameworks and logical tools, researchers are teaching computers how to search for parts of a proof all by themselves. This is a massive step forward for tackling the most complex and error-prone parts of making sure a system is correct.
Now, the other goal, unification. This is where things get really cool, almost sci-fi.
The big idea is to create something called Foundational Proof Certificates, or FPCs. The best way to think about an FPC is like a universal translator for proofs. It would let one proof system check and totally trust the work of a completely different system. Imagine creating a shared global foundation of verifiable knowledge. It's a huge deal.
And listen, the field is just buzzing with other ideas. We don't have time to dive deep into all of them right now, but you've got all these different creative ways people are trying to make proofs more flexible, from mixing calculation right into the logical steps to designing entirely new foundational structures. It's a really exciting space.
Okay, I know we've been talking about some pretty abstract stuff. So why does any of this actually matter outside of a computer science department? Why should you care about making proofs more flexible?
Because bridging this gap, well, it's absolutely critical. It's what allows us to build software with mathematical certainty that it's secure and that it's reliable. It's essential if we ever want to create AI systems that we can genuinely trust and verify. This work strengthens the foundation for all future technology and even opens up wild new possibilities, like having computers write their own programs that are guaranteed to be correct from the start.
And all of that leads us to this final thought. The goal here isn't just about making proofs a little easier to write. It's about creating a more seamless, a more powerful collaboration between our minds and machine minds. So the real question we're left with is this: if computers can start to reason with some of the same flexibility and intuition that we have, what incredible new worlds can we build together?